who is watching this video. My name is Olenjolai from beautiful country that called United Republic of Tanzania. I'd like to thank you for welcoming me in your house, in your smartphones, in your iPhone, in your computer, in your iPad, in your smart TV, in your desktop computer, in your laptop. So I'm very happy to welcome you to be part of your contents. So even myself, I'm very happy to welcome you into our Tanzania Online Advanced Secondary Schools in square bracket OLENJOLAIM. This is an online program, so it's online schools. We don't have any physical schools, but we are training advanced students, and our main area of focus is for the Tanzania. I mean that for the advanced students who are pursuing scientific courses in United Republic of Tanzania. Also, we have our YouTube channel that's called Tanzania Online A-Level Secure Schools in square bracket OLENJOLAIM. Before even you go through this session 11 or lecture 11, I would like to encourage you to watch one of the session, which is called the session 00, the general introductions of advanced physics for the Form 5 and Form 6, where I have given you too much of information about administrative of this program, so of this online program. Not only administrative, but also declare the publicly the vision that we have in this. But I can repeat, or I can just see, yes, I can briefly do a vision, a repetition. It means that I can briefly state the vision for these online programs, because that's what makes us to be different from even other programs that we have on the planet Earth. The main vision that we have, we like to prepare a community of Tanzanians and even Africans, and even in some other countries, who will be ready to take the classroom instructions and combine with a spiritual knowledge or spiritual knowledge in order to solve real life problems. So our main focus or our main objective to see students they are solving real life problems, even if by using the small the small knowledge that they have, because that is why we are born. We are born into this world in order to solve problems. We didn't come to this world to do visitations. We are not visiting here, we are not doing just like tourism. We are no longer tourists in this planet Earth. We just came to solve either single problems or more than one problem. So regardless that whether it is a single problem or more than a problem, but we are happy to see that students, they can solve real life problems once they graduate or even before the graduation. There are different levels of real life problems that everybody can solve. So for instance, these online programs and even the programs that I'm doing, I'm solving a problem. I might be even solving problems because I have more than 60, I have 60 platforms where I teach online. So it means that I'm solving more than a problem. But one of the problems is learning the scientific subjects and mathematics for advanced level. This material might be used worldwide in any continents, in any country, in any schools, in any regions, in any city, but our main focus will be using the syllabus of United Republic of Tanzania. That's our main focus. But what we'll be teaching about electrostatic is common. So the electrostatic I'll be teaching you is commonly even with electrostatic, which has been learned maybe in Washington, in London, so in different countries, in UK, okay, in Israel. So they are still learning. Electrostatics is common worldwide. So that's why I told you that these contents might be used worldwide. But the point of focus is by the syllabus of advanced physics for advanced secondary educations in Tanzania for 5 and Form 6. So well, in this online school we have 3 departments: departments of advanced physics, advanced mathematics, advanced chemistry. Those are the 3 departments that you have. And today we are in departments of advanced physics, and the main topic is called electrostatic. And these contents are for the Form 5 or Class 13, or Pre-Form 5, or Pre-Form 6, or Class 14. And also these contents might also be helpful to the Form 6 student or Class 14 students. Also, this material might be a reference material, so might be useful for diploma students who are pursuing science courses or science program. You'll find that this material will be helpful for them. So for example, diploma students, they may enjoy also in engineering, so in science courses, they may enjoy the beauty of physics in this YouTube channel. So today we have a topic of electrostatic, and this is sessions or lecture 11, which is called electric field. So that's what we want to teach you. If you remember, in session 1 of electrostatic, I introduced to you 5 topics of electrostatic, because electrostatic is the main topic. The first one was general introductions of electrostatic. The second one is electric force. Okay, electric force. So we call it electric force. Electrostatic force. So we call it electrostatic force. And the third one is electric field. So today I'm going to teach you for the first time about the third topic, which is electric field. It's very interesting, but there's a lot of assumptions and it's a little bit challenging, but it's very interesting because electricity is everywhere. So even our hearts, they pump blood because of electricity, right? So you find cars that we have that they can travel during the night because of electricity. We can work even during the night in the middle of the darkness if there's no moon because of electricity. So that's why I said that this is a very interesting subject, and especially for those who are expecting to take electrical engineering, and even those who expect to take computer engineering, mechatronics engineering, telecommunication engineering, electronics engineering. This is a very interesting topic for them. So let us go to the business. Just to do the quick review in electric force. Okay, so you've been solving problems. So in the previous lecture, we ended on solving problems. Problems, it means problem solving. Okay, problem solving in 3 laws. 1, fundamental law of electrostatic. Fundamental law of electrostatic, right? Fundamental law of electrostatic. And then the other ones is Coulomb's law of electrostatic. Coulomb's law of electrostatic. And hence we've been solving problems on superposition principle. Possibly you have not understood the problems that I've been solving clearly, but this is advantage of having a digital platform. So digital platform, you can revise the videos several times and lectures several times until the information has been written in your brain, right? So the materials are, for example, that this is session 11, all from session 0 to session 10, they are still in this YouTube channel. So you have to make sure you subscribe so that you get notification, because this is only session 11. Possibly in electrostatic, we might have even 40 sessions. I don't know exactly how many, but I know there will be more than 30 sessions. Interesting, right? Because we want to teach you, and we want this material to have present and future generations. Even my children, they might be using these programs, if God wishes, right? So we have a terminology called electric field. So you have to understand, we have a term we call electric field. We have a term we call electric field intensity. We have a term we call electric field strength. And then we have a term that we call electric potential. We have a term we call electric potential energy. We have the terms that we call the potential energy. So you have to understand these terms, and you have to take them slightly, right? So now I'm going to start with the terms called electric field. So listen carefully. Also we have a term we call electric flux. Say electric flux. So you can even sometimes pour out the saliva. So the fundamental question, you know what the fundamental question for Olenjolai? It is, I think you know. What is it? What is electric field? Before I take you in details, you have to know first, what is this term? Because it is new. Have you ever heard electric field in your life? And if you have never heard electric field in your life, get prepared that you can call your firstborn electric field, right? So what is electric field? Simply, there are many definitions of electric field, right? There are many definitions of electric field. I want to give you some of interesting electric field. Okay. So from a dictionary, or Oxford Dictionary, you can define electric field in this way. Electric field is a region. This is a region, okay? It's a region around a charged around a charged particle. Around a charged particle or object. Or object within which a force, okay, which a force will be exerted okay, on other charged particle. On other charged particle. On other charged particle. On other charged particles or objects. So electric field is the regions around a charged particle or object within which a force will be exerted on other charged particles or objects. That's one of the definitions. So electric field is the region. First of all, this is the region. So whenever we talk about electric field, think about a region. But which region? A region that's surrounding a charged particle. Surrounding a charged, around what a charged particle or a charged object, within which a force will be exerted on other charged particle or objects. Did you understand? First of all, to have electric field, we should have a charged particle. For instance, this positive charge, right? And then, so we say that, okay, so this is the charged particle. So electric field, for example, that the positive charge, I'll draw it for you, but the positive charge is just like this one. So electric fields are moving away from the positive charge. So this region surrounding this positive charged particle, for instance, suppose that this is the positive charged particle, right? So the region surrounding this positive charged particle is what we call electric field. So even around this way, whether in this directions or this directions, that's what we call it in physics, electric field. And then another piece of information that in which the force is what? In which the force will be exerted. So it means that these regions also of a charged particle, what happens? We can find a force, and that force is called the electric force, right? So it means that you can exert a force on other charged particle. What does it mean? We say, for example, from fundamental law of electrostatics, if you have a positive charge and positive charge, they do what? Repel, right? So in order for these two like charge to repel, it means there is a force. So how will it means these charges will repel these regions? We call it what? Electric field region. So if this charge brought closely together in such that they are in the electric field strength, the electric field interface or regions interface, then that the time that we'll experience that there is a force of what? Repulsion. Otherwise, there's no any force exerted. So the repulsion force is this charge, for instance, that this is Q1 and this is Q2. So Q1 exerted force to Q2 and Q2 exerted force to Q1. But the meaning of 40 exerted force or ability of the charged particle to exert force. Right? Some of other definitions which I don't recommend, which is saying that the electric field is the regions where the electric force is experienced. Or electric field is a region where the electric force is what? Experienced. So the regions where electric force is what? Is experienced. So that is another definition of 40 of electric field strength. Electric field, excuse me, not electric field strength, electric field. Okay. Again, do you need any other definition or is also enough? Okay. Again, we can define this way. Or electric field is an electric property. Is an electric property. Is an electric property associated with each point in space when charge is present in any form. When charge is present in any form. When charge is present in any form. That is another definition supporting of electric field. So it's an electric property. It's an electric property. Okay, it's an electric property associated with each point in space when the charge is present in any form. That is the definitions of electric field strength. The ratio of electric field lines of the force gives the directions of electric field. Against electric field is showed by the electric field lines. So electric field is shown by electric field lines. Okay, by electric field lines. So the direction of the electric field, ratio of electric field lines shows the direction of electrostatic force. Shows the directions of electrostatic force. So the directions of electric field lines show the directions of electrostatic force at that point. At that point. At that point. So now I would like to teach you the ratio of electric force. Directions of electric force or electric force at a point. We say that electric field is shown by the electric field lines, and the directions of electric field lines show the directions of electric force at that point. What does it mean? Most of these lines, or most of these electric field lines are curves. So it means that the tangent line at any point shows the direction. For example, that the tangents at this point, the tangents line. So if, for example, you have a curve, we are going to discuss this, maybe electric field lines. So it means that the tangent at this point will show the directions of what? Of the charge. Direction of the force. So here we say that I want to teach you about the directions of these electric field lines, or we call it Okay. So let me teach you about electric field. Electric field of 40 of charged particle. Charged particle. So I will show you this electric field of the charged particle in 4. So Roman 1, I would like to show you the electric field lines, okay, due to the positively isolated charged particle, due to the positive isolated charged particle. So the electric field lines due to the positively isolated charged particle. So we say that the electric field lines are moving away from the point charge. So this is, as I said, Roman 1, positive charged particle or object. What does it mean? Because we used to have a positive charge, we know that if you place with another positive charge, we just know that there is a force of mean that, because this electrostatic is all about the study of the charges at rest. So suppose that this is our positively charged particle, right? So the charge in this object is positive. So we want to see the electric field, right? So electric field of this charged particle will be moving away from the positive charged particle. So these are the electric field lines. Okay? Electric field lines. So these are electric field lines. So here again you have another electric field lines. Here you have another electric field lines. Here again you have another electric field lines. And here we have another electric field lines. Okay, electric field lines, that is. Wow. So you have several electric field lines. Okay, so these we call them electric field lines. Electric field lines. Electric field lines. So several of them. You have against another electric field lines. You have against another electric field lines, etc. Okay? So then this region now. This region. So let's say that this is what we call the electric field. So the regions where the electrostatic force is acting, so this is what we call the electric field. Electric field. So it's a region, electric field region. So that is, so whenever we draw, so from now onwards, whenever you draw the electric field for the positive charge, you have to bear in mind that they are always leaving the charged particle, right? Second type of the charged particle, because we have electric charged particle, is negative. So it's negatively charged particle. negatively charged particle. Negatively charged particle. So it's negative charged particle. You say that the electric field lines positive charged particles are moving. So excuse me. So you can read this line. Are moving away from the pointing charge. So you say that electric field lines of the negatively charged particle are moving towards the charged particle. Okay? So then, this is negative charge. It's negative charge. So with this negative charge, we say that you have this point charge, you have this point charge, you have this pointy charge, you have this pointy charge. So the electric field lines for the negatively charged particle, we are moving towards So remember that this also we call them electric field lines. Electric field lines. Then this region so these regions we call the electric field region. Interesting? So that is in case you have isolated. So this you call the figure 2, 1. So isolated what? Isolated the positively charged particle, and this is figure 2.2 isolated negatively charged particle. I wrote it in abbreviation. So to measure the concentrations of the students. Then we say that, okay, so that is all about isolated charged particle. Now, when you've been learning these concepts of electrostatic in the previous topic, then we learned, or I taught you, a law that's called fundamental law of electrostatic. So I told you that the likely charge attract each other, and unlikely charge attracting are repelled to each other. So then Roman 3, we want to draw the electric field lines of the repulsion or attraction force. So now we say that I have to draw for you about unlike charged particles. Okay, unlike charged particles. Unlike charged particle. Like charged particles. So he said that when two unlike charged particles are brought close to each other. Then there is the force of attraction due to interaction of the electric field lines. With the electric field lines. How the phenomena take place. So this is the sketch. Here we have a positively charged particle, and here we have a negatively charged particle. So unlike charge attracted to each other, and like charge repel to each other. So if you remember that, from the electric field lines of isolated point charge, the electric field lines of isolated positive charge are always leaving away from the charged particle. And the electric field lines of isolated negatively charged particle are always moving towards the charged particle. So even in this case, we have to take that consideration. So you are going to have electric field lines that will be interacting. So this is possibly will be providing the electric field lines, and this is the fundamental concepts of understanding the behavior of electric capacitors. So again, here we have another electric field lines, which are curves, not a straight line. And also here we have another electric field lines. It's a curve. I guess here we can have another electric field lines. It's a curve. We can have another electric field lines. It's a curve. And then we can have another electric field lines. It's a curve. Then we have another electric field lines. It's a curve. Then we can have another electric field lines. Also it's a curve. Then we can have another electric field lines. This also, it's a curve. Right? So those are the point charge. So this we call it figure 2.3 are the electric field lines. Electric field lines of unlike charge. Unlike charges. So these lines, including these lines, including these lines, including these lines, we call them electric field lines. And these regions we call electric field. Called electric field. Called electric field. Okay? So you go for Roman 4. Okay, electric field line. Electric field lines of like charged particles. Like charged particles. Like charged particles. So I say when 2 like charged particle and two like charged particles, okay, are brought close together, they repel. They repel. Due to what? Why do they repel? Due to interaction between the electric field lines. In the electric field lines. So we have two cases here. The first case, we have negatively charged particles, So we have negative, so you have to stop writing. Look the forces, or why do they fail to attract each other. So these are the reasons why we have fundamental electrostatic law. So these are the origins. This is a clarification that why we have that fundamental law of electrostatic. So we say that for negative charge, we say that the electric field lines are moving towards it, right? So it means that if for this guy, what's going to happen? So it will have electric field lines which will be moving towards it, not away. So these are the electric field lines moving towards it. So against here some other electric field lines. Here you have against other electric field lines. And you have other electric field lines. Then you have against other electric field lines. So then this is like that. And hence you have this field, this field, this field. And then on this side, similarly also, the electric field lines will be moving towards the negative charged particle. That's why there is a force of 40 repulsion. The force of repulsion, there's a repulsion force between like charged particle. So this guy, this one, this one, this one, and this one. So you have this guy, this guy, this guy, this guy. Okay? Oh, excuse me. This is towards. This is towards the negative charged particle. Okay. So towards. So then this point, we call it neutral point. Why neutral point? No any electric field strength. Called neutral points. No any electric force at that point. So also this one, or these lines, this we call them electric field lines, electric field lines. Similarly, this we call them electric field lines. Electric field lines. So that is experimental demonstrations of fundamental electrostatic law. Then B, let us see that the appearance of positively charged particle, appearance of the electric field lines of positively charged particle, positively charged particle, positively charged particle. So for positively charged particle, let us see the spacing or the distribution of electrostatic force. Okay? So again here, there's a repulsion in these like charges. So because of repulsion, you find that there is no attraction between it. There is no joining of 40 of electric field lines. So let me draw this one and then I'll generalize. I'll generalize with the field lines of 40 of unlike charges. So wonderful enough. So electric field lines living away. So here they are living away. They're living away. They're living away. In this case also electric field lines are living away. Living away from the positive charge. Living away. Living away. In this session, you'll be drawing different figures of 40 electric field lines. And this point in between we call it neutral point. And this out, these are electric field lines. And this entire region is called what? Electric field. So listen carefully. According to the fundamental law of electrostatics, it states that unlike charge attract each other. Stop writing if you're writing, listen carefully. I want to explain something here. Unlike charge attract to each other, and like charge repel to each other. So from this spacing or the electric field lines spacing, okay? So you see these are like charge. Why do they attract to each other? Because for suppose that this is the midpoint. This is the midpoint. This is the midpoint between positive charge and negative charge. Right? So if you cut at the midpoint, you'll find that this positive charge is producing or is providing what? The electric field lines. And the negative charge is receiving. So if you cut here, for example, that you separate, this positive will be continuously providing what? The electric field lines, while the negative charge particle receive the electric field lines. So you see that they after interaction. So when they interact, it means that the positive will be supplying the electric field lines, and the negative will be receiving the electric field lines. So that's why we have attraction between the unlike charge. We say like charge according to fundamental law of electrostatic repair. This is negative charge, and this is negative charge. Negative charge receive what? Electric field lines. And this also receive receive what? Negative, receive what? Electric field lines. So none of them are providing electric field lines. So what happens? So this one is receiving, this one is receiving, right? So it means that the electric field lines are towards itself, right? Are towards what? Itself. So because the electric field lines will be towards itself, so each of them will be carrying its own electric field lines, and there's a strong repulsion. Why? Because this is electric field lines that going in these directions, and this is the electric field lines that going in this direction. While in case of attractions, these are the electric field lines going in this direction, and this also electric field lines going in the same direction. So here the electric field lines are going in the same direction, and the electric field lines are going in the opposite direction. So that's why there's a strong repulsion force there. And this is the neutral point. What does it mean? It means that, as for example, if you be trying to push this charge to come close to this one, then you find that the charge is rejecting. So why? Because of repulsion, right? So for example, you are bringing them in this way, so you find that if you bring this one, there's a repulsion force. For example, in case of the magnet, if you can see. So for the magnet, for example, you have a piece of ions. What happens? So a piece of ions will be attracted towards the magnet, right? So it means there's interactions of the field lines, which call this magnetic field lines, right? But for example, if you have a wood and then you place near the what? To the magnet, however, that there's no any physical repulsions but no any attractions. Why? Because even if the wood contains the field lines and the magnets contain the field lines, no interaction. So here there's no any interaction. Similar to this point. Positive charge is always means that generating the field lines towards it. So this one generates towards it and this one towards it. So because it generates towards it, then it's difficult. None of them switch receiving the field lines from the other one, right? So that's why that there's a strong repulsion force. And that's why that here we have a neutral point. Are we together? In case you have any question, don't hesitate to ask in the comment section. But that's the general overview of the electric field lines and the electric field. Okay. So let us continue. So you see, I believe that you have been introduced to this concept during your O-level education, but you didn't learn this stuff because we wanted to encourage you. So you reached the advanced level, at least that now say, yeah. So you have a new terminology there, if you have realized it. And this terminology is electric field, or electric lines of force, or electric field lines. Electric field lines. Electric field lines. Or we call them electric lines of force. Electric lines of force. Electric lines of force. Fundamental question. What is electric field line? What is electric field line? What is electric field line? I want to give you at least two definitions. Field lines. What are the electric field lines? So electric field lines, electric field lines are imaginary lines. Imaginary lines, or these are imaginary curve. Or imaginary curves drawn through a region of empty space. So that its tangent at any point is in the direction of the electric vector at that point. So he said that we give you some time to copy. Again, in case that you feel from your heart you want to offer a sense-giving offering in order to be a part of these programs, or in order to contribute for the running cost of this program, you may send your sense-giving through that telephone number 0759745331. Actually, the contents of the material that I'm teaching you, if I could charge you, I could charge you a lot of money. They are very expensive. Okay? So we think that electric field lines are imaginary lines or imaginary curves drawing through a region of empty space, so that its tangent to any point is in directions of electric vector of that point. Do you understand? We say that these are the imaginary lines. When I say imaginary lines, you cannot see them on your eyes. If, for example, you have a charged particle, or maybe a substance which contain, for example, maybe you have an ion. So an ion contains electrons, right? So it's a charged particle, for instance. Okay? So, in case that we say that we want to see these lines, we cannot see them by using our naked eyes. So what happens? So why? Because they are imaginary lines. So these are just the Gaussians who did a lot of experiments on this, and the one that said that there's imaginary lines. And that's why that, for example, if you remember, when you'll be learning physics for the Form 4, then you find that sometimes that there's a piece of paper, we put something like a magnet, and then you can draw lines. It means that lines maybe on these sides, according to how the spacing is taking place there, right? Okay, so that is, so he said these are imaginary lines through a region of empty space, so that its tangent to any point is in the directions of what? Of the electric vector at what? Electric vector at that point. Or, in other words, we say that electric lines of force is the lines at which the tangent to it is the directions of the force on the small positive charge at that point. So simply we say that also, or are the lines of force are the lines of force, of electric force, are the lines of electric force so the lines of electric force, okay, in which the direction are missed, in which the tangent line, in which the directions of the force, in which the tangent line on them shows the direction of the force, direction of the force at that point. So these are the lines of the electric force in which the tangent line on them shows the directions of the force. Shows the direction of the force at that point. And lines of the electric force in which the tangent line, the source lines, shows the directions of the force at that point. What does it mean? This means like this way. For example, suppose that this is the electric field lines. It's electric field lines. So suppose that this is electric field lines. What does it mean? Electric field line, right? So when you say a tangent line, it's a line which touches a curve at only one point. That means of tangent line. So for instance, if you draw a tangent lines at this point, then this tangent line will show directions of 40 of these field lines of this force in this way. So this is the direction. So this is tangent A. Again, if you draw a tangent line at this point, like this way, so this is E tangent line B. So for this, at this point A, for instance, that if this is the A, it's the point of tangents, then you find that the direction of electric field lines is this way, right? And then for this point to be, the directions of the field lines is this way. Again, if you draw, possibly the tangent lines at this point C, the directions of the field lines is this one. Right? So this is means of the electric field lines. First of all, they're imaginary lines, but the tangent at any point along that field lines show the directions of 40 of the force. Show the directions of 40 electric vector. It means that if electric, because the electric field is a vector quantity, just like a force. Electric field strength is the vector quantity, right? It's not a scalar quantity. How many examples did you end yesterday? How many examples did you end in the previous session? 13. So this considers example 12. refer, advanced certificate secondary education examination of 2001. So we have this case, sketch the electric field lines patterns for one point charge, point positive charge, point positive charge, Roman 2, point negative charge, Roman 3, pair of parallel conducting spheres, parallel conducting spheres or plates. When one plate has positive charge, and another has negative charge. Negative charge. So we say that sketch the electric field lines patterns for the Roman 1 point positive charge, Roman 2 point negative charge, Roman 3 pair of parallel conducting spheres or plates when one plate has positive charge and another has a negative charge. So for Roman 1 and 2, refer the notes. Roman 3, at least it's a challenging one. That's not a challenging one for students who love physics. So Roman 1, so solution. Roman 1 and Roman 2, refer notes. Refer what I taught you in this session, session 11. Then Roman 3 now, I can help you to solve, you. Because I want to add something. These questions add a new concept in your mind. Parallel, a pair of 40, a pair of parallel conducting spheres or plates. What does it mean? These are we call them electric conductors, right? Electric conductors. They do conduct electricity. So one is positively charged, and the other ones, or one plate is positively charged, and another plate is negatively charged. So what does it mean? So it depends. We can draw these plates possibly like this way. This is the positively plate. You can draw them as the cylinders. So that the first plate, then this is the second plate. Right? And this is positive charge. So listen carefully. Here this is the foundations of the capacitor, because capacitor is nothing, just contain two parallel plates, which one is positive charge and the other one is negative charge, right? So listen, so here this is positive charge, this is negative charge. So this is the positive charge, just like a point charge. what the directions of electric field lines from the positive charge. Are moving away from the positive charge, right? And what the directions of electric field lines for the negatively point charge. They are moving towards. So if that's the case, the electric field lines will be moving downward from positively charged plates to the negatively charged plates. So from positively charged plates, the negatively charged plates. So positively charged plates to the negatively charged plates. So this is positive charged plate to the negative positive charged plates to the negative charged plates. Okay? So this is the case. Okay? So these are positively charged, this is negatively charged. So these are the two plates. Plates of 40, or call them, yes, plates of conductors. Okay, if you have any question, you can ask me in the comment sections. But this is how the stuff goes. Maybe students can ask me questions. What if you have negative plates? So it's no. So you know that the field lines will be like when you have 2-point positive charge. So they repel. If you have also positive plates and positive plates, they repel. So now let me take you into another interesting point, because this lecture today is all about electric field lines, and also I'll teach about electric field intensity or electric field strength. That's all. So I have 3 concepts that I should teach you in this lecture. It's a little bit long lecture, but I'll break these videos into session 11L and possibly 11B and possibly 11C. So you have to watch all the 3 sessions before you go for session 12. So then we go for the next part, we call it properties. Tell me in the comment section if you enjoy learning electrostatic. Properties of 40. Properties. What are the properties of electric? What are the properties of electric field lines? What are the properties of electric field lines? What are the properties of electric field lines? Right? What are the properties of electric field lines? What are the properties of electric field lines? Properties of electric field lines. So you say that there are some properties of 40 of electric field lines. So I'll teach you some. Number 1. So one of the properties say that when we have 2 parallel plates, the lines of electric force start from positive charge and ending to the negative charge. So when we have 2, that's just an example, charged particles. When you have 2 unlikely charged particles. 2 unlike. When you have 2 positive and negative charged particles, so when we have 2 charged positive and negative charged particles, then the electric field lines move from positively charged particle positive charged particle towards the negative charged particle. Okay? So when we have two positive and negative charged particles, then the electric field lines moves from positive charged particle towards the negative charged particle. Right? So for example, parallel plates, like this. Okay? So parallel plates. So that is the property of electric field lines. So one is electric field lines generator. So the positive plates is electric field lines generator. So this is generator electric field lines. And this is electric field line receiver. So you see, so this is what we say. So this is electric field lines. That's the first property. Number two, the second property. Any tangent line at any point of electric field lines indicates the direction of what? The directions of electric field at that point. For instance, that this is the electric field. This is the electric field strength at this point. So this is point B. So that is electric field strength, point B. So we have discussed about this one, that in a tangent line will show directions of electric field strength or electric field. So that's the second property. The third property, can you tell me? You can pause the video and then write on the piece of paper, and then you continue watching the video if you are right. The third property, we say that electric field lines are never close to each other. So these electric field lines are never close to each other. What does it mean? You'll never find electric field lines which have been drawn in this way. For instance, you have a set electric field lines here, and then you have the other ones in this way. You will never find this case. Right? So they never cross each other. They are parallel, but they never cross each other. Against the fourth strong property, say that electric field lines cannot pass through the conductor. That to say that electric field strength, electric field inside electric field inside the conductor is 0. Electric field inside the conductor is 0. That's the point that you have to make. What does it mean? For example, suppose that this is a conductor, current carrying conductor, so we call it or a electrical conductor. And then suppose that this is the electric field, right? Listen careful, electric field. So when it will strike onto this conductor, electric field will not have ability to pass through this conductor to appear on the second part of the conductor. So electric field strength or electric field lines or electric field inside the conductor is 0. For example, this is an iron. Okay? So for instance, an iron is a good conductor of what? Electricity. Okay? It's a good conductor of electricity. So electric field strings or electric field lines, they cannot penetrate through what? The conductor. So if it is the conductor, for instance, that the conductor is the conductor AB, right? Conductor AB, then we say that electric field strings cannot pass through that conductor. The fifth property say that the electric field lines, you have to understand these electric field lines, because when I will be teaching about electromagnetism, I will also teach you about the properties of magnetic field lines. So these are electric field lines. Remember that we have a certain principle and a certain concepts and belief in physics and even in engineering. Whenever there's electricity, there's a magnet, and whenever there's a magnet, there is electricity. So now I'm teaching you charges at rest. The next topic after electrostatic, I'll teach about current electricity, then I'll teach about alternating current, and then I'll teach about magnetism. So stay connected. So the electric field lines are perpendicular electric field lines are perpendicular to the surface. To the surface of the charge. Perpendicular to the surface of the charge. So electric field lines are perpendicular to the surface of the charge. So that's the fifth property. The sixth property say that the magnitude the number of lines is directly proportional to the magnitude of the charge. The magnitude of the charge. So the magnitude of the, so you say that the number for electric field lines is directly proportional to the magnitude of the charge. The number of lines, the number of electric field lines, the number of electric field lines is directly proportional to the magnitude of the charge. The number of electric field lines is directly proportional to the magnitude of what? Of the charge. So it means that the quantity of charge is directly proportional to the what? Number of what? Of electric field lines. So for example, if the quantity of charge is 2 microcoulomb, it means that there's few number of lines compared to the quantity of charge which has 10 microcoulomb. Right? That's the point that I want to make. So we say that to separate from each other which like charge close to each other. When like charge close to each other. So you have the seventh and the last property, you can look for the rest. When the like charge, when the like charges or like charges are brought close to each other, then the electric field strengths or the electric field lines tends to expand laterally. What does it mean? It means that when you have, for instance, positive charged particle, we have discussed this phenomena, you find that inside of these field lines to come close, then you find that they're expanding laterally. So expanding laterally, it means that each field lines is running away from the other field lines, right? That's the means of lateral. So they tend to separate from each other. So to expand laterally means that to separate, lateral means that to separate to each other. That's another property of these electric field lines. That if you have positive charge, with a positive charge have been brought closely, so this one is leaving, right? So these electric field lines are leaving in this direction. Okay? So just like this. So this is the neutral point. Okay? So because this is the neutral point, we say that this is the tendency. So these field lines, they have a tendency of separating each other rather than attracting each other. Okay, so that's all about electric field lines. Electric field and the electric field lines. I believe that you've got something new, and then you are ready now, so I can take you to the next phenomena, which we call electric field line or electric field strengths. Electric field strengths or electric field intensity. It's called electric field strengths or electric field intensity. And we have always common fundamental question of Olenjolai. What is electrical fielding? What is electrical fielding strength? What is the meaning of electrical field strength or electrical field intensity? What is electric field strength? So you can take a few minutes and then ask yourself, what does this terminology mean? What means of electric field strength? Okay. So let me define for you. So an electric field strength I'll give you at least 2 to 3 definitions. An electric field strength we say that it is a measure of the strength It's a measure of the strength of an electric field at a given point in space equal to the force that the field will be induced on a point charge. Induced on a unity of positive electrical charge. On a unity of positive electrical charge at that point. Also called the electric field intensity or electric intensity. So electric field strength, so electric field intensity is the measure. So this is the measure of what? Of the strength of what? Of an electric field. So we measure strength of electric field, which I've already taught you, okay, a few minutes ago, at a given point, not at every point, at a given point, equal to the force. So this is the mathematical formula. The force that the field will induce on a unity or positive electric charge at that point. So now, if you remember in previous examples, for example that we used to ask you that to find electric force at point X, and that point X does not contain any charge, right? And we used to let the charge at point X to be a unity charge of of 1 microcoulomb, so 1 nanocoulomb, right? So why? Because our primitive focus is on what electric field strength. So electric field strength, we say that this we determine by taking the magnitude of the force between the two point charge, and then we divide by a unity positive tested charge. So it means that we do computations with the reference of unity positive charge. What does it mean? Because we realize that a charge itself, like this one, a charge itself, it can what? So it contains what? It can give us what? Electric field, right? Electric field. So in order to get electric field at this point, we should also take, suppose that here we have 1 microcoulomb, a unity charge, right? So to know the electric field strength between these points. So if that's the case, listen, for example, we have a positive charge, we say that the field lines are living away from this positive charge in this way, right? In this way. So for instance, we want to determine the electric field at this point B. So we have to make that, we have to let that here we have a unity tested positive charge. Why should we let that one? In order to determine the magnitude of electric field strength at this point B. So a unity charge or a unity positive charge is a reference charge. So it means that if we want to determine the electric field strength at any point due to the charged particle, then we make assumption that let us assume we place a unity charge at that point. What will be either the force of attraction or force of repulsion. However, that there is no point there. Do you understand? So that's why that we say equal to, so this is a kind of mathematical language now, equal to the force that the field would induce on a unity of 40 positive electric charge at that point. Right? Okay. So that's one of the definitions of electric field strengths. Or, the second definition, we say that electric field strength, say 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 electric field strength. So electric field strength, we say that is a strength, okay, electric field strength is a quantitative expression. This is the quantitative expression. This is the quantitative expression of the intensity of electric field. Electric field at a particular location. At a particular location. So you say that electric field strength is the quantitative expression of the intensity of electric field at particular location. So this is the quantitative expression of intensity of electric field at particular location, mathematically. This is quantitatively or qualitatively definition. So now let us go to quantitatively, mathematically. Say that the electric field strength, is defined as what? As electric force, as the ratio electric force between charges to the positive charged particle, to the positive charged particle, to the positive, the point charge, exactly, to the positive point charge particle, the positive charged particle. So you can define like that once. Okay? So how do you define it? Electric field strength, also it is donated, before even I read the formula, it is donated as this. It's a vector quantity. What does it mean? So we say that the electric field strength donated by capital E, field strength is a vector quantity. So in our notation, we have this symbol. So you say that now electric field strength, this is equal to what? Electric field strength, we say that is equal to electrostatic force of what? Of a quantity of charge Q. Remember, even the force, it's a vector quantity. It's a vector quantity. So this one, because the point test charge can just have Q naught, right? So we say that where F is representative electrostatic force Q naught, this is point test charge, point charge. This one represents electric field strength or intensity. So remember that in case of electric field intensity, now we don't need the two charges to attract each other. We just need what? We just need one point charge and another and any other point. That means of electric field strength. What does it mean? In electrostatic force, for example, that we can say Coulomb's formula of electric field strength, electric field intensity. So Coulomb's formula of electric field intensity, how do we get it? First of all, recall Coulomb's formula of electric force, that means of CFF, Coulomb's formula of electric force. What did we say? We say that suppose we have 2 point charge. This is what? Q1 and this is Q2. Then we have a distance between them, or between the ear centers, which is R, right? So according to Coulomb's, we say that the force, which is vector quantity for that case, is equal to proportionality constant K times Q1 times Q2 over square of the distance. But this one, I told you, if you want to define such vector quantity, you should have a unity vector U, right? But we say that we'll be dealing with magnitude of force. It means we'll be dealing with magnitude of force. So even this one will be magnitude. So K, Q1 times Q2 over R square, right? And then U. So for electric field strengths now, listen carefully. The second step. To get electric field strengths, I told you that it's not necessary to have 2-point charge, right? So you can have only one charge, which is, let's say, Q1. It may be positive or negative. This is Q1. So then we want to find electric field strengths at this point, right? So then what are we going to have? We have a distance between the center of the point charge and the point where one determines what the point one determines electric field strengths, right? So we know that if this is positive, so you know the field lines that they'll be going this way, as I told you, right? So suppose that this distance also equal to R. So in order to find the field, the electric field strengths at this point C, let's say at point B, then we have to assume we have a unity positive charge here, right? So let us call this unity positive charge, we can call it Q2. But this is unity positive charge. We make that assumption, right? So according to the definition mathematical formula of electric field strengths, we say that it's a ratio of what? Of electric force, of electrostatic force to the point charge. It means that to the unity positive charge, test charge, solution. So if that's the case now, listen. So you say if this is the case, suppose that this is the first equation. So now we go for the, okay, so if that's the case, so now we say that electric field strength, we listen, from electric field strength, is equal to electrostatic force of attraction or repulsion of what? A point positive test charge, which for this case it is Q2. Right? So if that's the case, this will be the second equation. Is there a relationship between the second equations to the first? So okay, so before even we have second equation, we can take consideration, let us take consideration only the magnitude of electric field strengths. So similarly here we have a magnitude of force over the point, a unity positive testing charge, right? So this is what we call the equation 2, because it's scalar equation, scalar quantity contains scalar quantities, just like this one. Just like, okay, so if you have magnitude, then this directional vector has already been expressed. So then we go for the third step. The third step, we say that substitute equation 2, equation 1, not equation 2, equation 1 into equation 2. So then we say that electric field strength, this is equal to what? So we have magnitude of force is equal to proportionality constant times quantity of charge 1 times quantity of charge 2, right? And then divided by what? By R squared. But here we have divided by what? Q2. Right? So this positive test charge will cancel. So you have what? You have electric field strength. This is equal to proportionality constant times what? Times Q1 of what? Over square of the distance. So now, the mathematical formula we say that the Coulomb mathematical formula right now will be this one. So electric field strength is equal to proportionality constant times quantity of charge or voltage over square of the distance. Right? But also remember, from Coulomb's, K is equal to 1 over 4 pi permittivity of the medium. So suppose that this one is what is the third equation. So suppose also this is the fourth equation. So if we got the first step of our derivation, we might say that substitute equation 4 into equation 3. So you say that electric field strength or electric field intensity is equal to K. You don't have K anymore, so it's equal to Q divided by 4 pi permittivity of the medium R square. So this is another formula which might be useful. Right? Again, but we said that I told you in previous session, electric permittivity, this is equal to what? The electric constant times what the permittivity of free space. So we say that for air, if the medium is air, then we say that the electric constant is equal to 1. So if it's equal to 1, it means electric permittivity, for that case, is equal to electric permittivity of the free space. So we say electric field strength, this is equal to the quantity of charge of what? 4 pi, then permittivity of free space, and then square of the distance. Okay? So that's another formula. Again, if the medium is not air, means that we say if the electric constant is not equal to 1, so we say that then electric field strength for that case will be equal to the quantity of charge is equal to 4 pi the electric constant times permittivity of the free space, and then times what is square of the distance between the 20 charges. So this is another mathematical formula. So now electrostatics is getting so much interesting because now we are discussing or we are enjoying the beauty of physics. Okay. So I would like to, this will be example 22, which is homework. This is homework 11. By using dimension analysis, dimension analysis that I taught you in measurement, the dimension analysis. Okay. Deduce the following. Deduce the following. One, dimension of electric field strength, and two, SI unit of electric field strength. I believe that you enjoy the beauty of physics now, because when physics turns into formulas, questions, equation, then physics getting very interesting. For the lovers of physics only. You love physics? Tell me in the comment section. I know the answer of many students because about physics, because physics is causing some troubles for them. They have to think differently. Otherwise, that the business become a little bit tough for them. Okay, so I like just to say electric field due to the group of pointing charge. Okay, so this is the last concept. Electric field, and through this last concept now, electric field due to group of charges. Electric field is intensity, strength. Electric field strength due to the group of 40 to the group of charges. With the group of 40 of charges. Electric field strength to the group of charges. With the group of 40 of charges. Electric field strength to the group of charges. Electric field strength to the group of charges. So before I teach you about, I think that is okay, that the interesting part. So here we say that from the superposition principle, that I told you in previous session, from the superposition principle, we say that the resultant electric force is given as this. Is equal to the square root of summation of horizontal components of force plus summation of vertical component of force square. Okay, so similarly, means that this is equal to what? This is equal to the square root of what? So similar, because this is the summations of the forces in the horizontal components. So you can have also summations of the electric field in the horizontal component. This is square, and also we said that summation of the electric field in vertical component square. Right? So this is what we have to use. So in case that you find one point charge, it has been surrounded by the several charges, and then you want to find electric field. So as I told you, usually you should find the electric field in horizontal components, and also you should find the summation of electric field in vertical components. Sign. So to find the resultant, so similarly, resultant electric field strength, is given as that formula, But also, for instance, if you have, let's say, several resultant forces, this is just generally, you can have resultant force 1 plus resultant force 2 plus resultant force 3 plus this to resultant force n. This is just in addition, right? So sometimes we say that, okay, fine. So it means that the resultant electric field, this will be equal to what? Summation of what? Electric field when I is equal to 1 to n. Right? So sum of 40, sum of electric field, okay, whether this is a resultant electric field. So this might contain horizontal and vertical, horizontal, vertical, horizontal, vertical. We form resultant, but maybe have several, okay, several point charges. Okay? So that's the resultant electric field strength. Okay, so sometimes you can find that even this formula we can express it as 1 over 4 for free space medium, or the material of free space, right? The material of free space. This one, and then we say that summation of what? Summation when I is equal to 1, and then here we have quantity of charge, which is Q, and this Q is, maybe it might be 1, 2, but you want to look in different points, and here we have I squared. So this also you can express this formula in this format. Right? So here it is just nothing, because you remember that this formula is just like this one, where the rate constant is 1. So 4 pi per material of the free space, these are constant. We took them out of summation. This is the sigma notation, right? So what might be changing is only the distance. What does it mean? For instance, we have a point charge here. We have a positive point charge. Then you want to know electric field here, electric field strength here at this point. Okay, then at this point. So it means that these are different values of 40 of distance. So suppose this is R1, this is R2, this is R3, this is R4, this is R5. But this is only a quantity of charge Q. It's quite different from what I taught in electrostatic force. Because we used to find that several point charges surrounding one point charge. For electric field strengths, we just need one point charge. But we can find electric field strengths or intensity at different points surrounding the point charge. So that's why that we have this formula. It doesn't mean that you can find problems which demanding like this, but it's better if I give you the general concept in case that you encounter it, you know how you can navigate through it. So that's why that only this R is the one that varies. Q is the same, right? So quantity of charge here is the same. Why does this R vary? Because you want to find electric field strengths at different points from this reference point. So this point, the distance from here to here is not equal to the distance from here to here. And the distance from here to here is not equal to the distance from here to here. And the distance from here to here is not equal to distance from here to here. So it's the same quantity of charge, but you are finding the electric field at different points. If you understood? Okay. So if that's the case, okay, so if that's the case, I would like to say that this is the end of session 11. I've been teaching about 3 concepts: electric field strengths, electric field lines. And then I introduced you a little bit about the parallel plates, and I clarified to you about the fundamental law of electrostatics, that like charge repel and the unlike charge attract to each other. So that's what I have taught you in this long session or long lecture or long period. And you have to expect that I will break these sessions into 11A, 11B, and even 11C due to their size, right? So you have to make sure to go through session 11A, 11B, 11C before you go for the session 12. So I would like to invite you to join me in the next session, that will be session 12, where now I'll be solving problems regarding on electric field intensity. I thank God who have been with me during the preparation, even during this time of teaching. And also thank God who have given you an opportunity to join me and even to take your route on these programs, special digital program. And I'll keep on praying for you, and I ask you also to keep praying for me, so that we may do the will of our Father before we departure on from this world that we are living by. Make sure that you have to remember to subscribe so you get notifications once we upload any new video. And make sure you do the homework, all the homeworks that I've left for you yourself. Try yourself, don't worry to make mistakes. You know that there's a phenomenon there's a phrase we used to say that practice makes better. So make sure that you practice several times. You should have the reference book, which I mentioned in session 000, introductions of advanced physics for Form 5 and Form 6. Make sure you have the reference book, you go through them, so you read these topics from some of the advanced physics books, and you do some exercise, you solve examples contained in that book, you take the past papers, you can check that some questions have been asked, so that you'll become competent as time goes. It's a process. Learning physics and mastering advanced physics is not an easy task. It's a process, it's a long-term process. So you have to be patient when you're being learning. Don't think that if you spend the whole night, the single all night, then the next day or the next morning, you are competent in advanced physics. I want to tell you that it doesn't work like that. Okay? So also share these contents with your classmates so that they might know there's something already in their hands. Right now, so these programs mean that every student across the country of the Republic of Tanzania, he or she should get valuable and even modern advanced secondary education without having a physical interaction with the teacher who is going to teach you. So I invite you in the next session. Let us meet there. So I'll take you from one point to another point as God blesses us step to step. Stay tuned, stay focused, stay connected. Let us meet in session 12.